This video is a continuation on limit points. We're going to do a few examples and also prove a new theorem. So recall we defined in the last video that if xd is a metric space and A is a subset of x, then a point x in the set X is a limit point of A if every open set containing X contains some element A in A such that A is not equal to X. So, our picture for this, X might be in A, X might not be in A, or X may be in A. And what it's saying is that every open set containing X, any open set U, contains some other element A that is in the set A, is not equal to X, and is also in the set U. Similarly, our picture could look like this. U prime for this different X and some other point A. So that's our picture for limit point. This is just a quick lemma. A lemma is sort of like a mini theorem. X is a limit point of A in a metric space xd if and only if for any epsilon greater than 0, there is some y in the ball centered at x of radius epsilon that is also in the set A and is not equal to the point x. So this is just using our previous theorem that U is open, a set U is open if and only if for any x in U there is some epsilon greater than 0 such that the ball centered at x of radius epsilon is contained inside of U. So in this previous picture that we have, we could say, okay, we're assuming that U is an open set containing X. That means there must be some ball centered at X of radius epsilon. That too is an open set that contains X, and so it must be the case that there's some other A inside of there that's not equal to X, meeting this same criteria. And for the reverse implication, of course, the ball centered at X of radius epsilon is an open set, so it must be true for any such open set, any such ball centered at X containing epsilon. So this is definitely true. You might wonder, why is it phrased in this more general setting? Later, when we talk about topological spaces that are not necessarily metric spaces, we'll need to use this more general definition that does not rely on the concept of distance or ball centered at X. Okay. But for now, this can be sort of a useful way to avoid an extra sentence in further proofs. We also, in the previous video, had a theorem that if xd is a metric space and A is a subset of X, then a point X in that set is a limit point of the subset A if and only if the distance between X and the set A minus X is equal to 0. So we already proved this. So with all that background in mind, I'd like you to try a few examples. I'd like you to give the set of limit points for the following subsets in these metric spaces. So first, we have the set Q, the set of rational numbers in the metric space of the real numbers with the usual metric on R. Next, the subset containing just the elements 1, 2, and 3 in the real numbers with the usual metric. Then the set of points 1 over n, such that n is a natural number. The natural numbers is the same thing as the set z plus, just the positive integers. Again, in the metric space R with the usual metric. And finally, the set 0, 1. So this is the set of open interval from 0 to 1, set of all real numbers from 0 to 1, in the real numbers, this time with the discrete metric. So I'd encourage you to pause and try these out, and we'll talk about them in just a moment. Let's look at these examples and keep in mind this lemma and this theorem that we mentioned up above. So for the first, we're looking at the set Q of rational numbers inside the real numbers with the usual metric. What we're actually going to show is that every real number is a limit point for Q. So let's let X be an element of the real numbers. Sorry about that. Let's let X be an element of the real numbers. What do we need to show? To show that X is a limit point of Q, we need to show that for any epsilon greater than 0, there is some y in the ball centered at x of radius epsilon that's also in the set we're interested in this case Q, the set of rational numbers, other than x itself. So let's let then epsilon be greater than 0. And if we need to show this above, let's consider this ball centered at x of radius epsilon. How can we show that there's some rational number other than x itself inside of that ball? Well, we know from our previous theorem 2.1, in general you don't need to refer to numbers of theorems, but I'm just referring in case you want to look back. This was an important one about the rational numbers and the real numbers. It tells us that between any two real numbers is a rational number. So that's an important fact about the reals and the rationals that we previously proved. So how could we use that in this setting? Let's consider, let's say then that therefore, there exists some y element of the rational numbers such that x is less than y, which is less than x plus epsilon, since x and x plus epsilon are both real numbers. So what do we know? So y is in both the ball centered at x of radius epsilon, and it's in the set we're interested in of rational numbers, but it's not equal to the element x itself because y is strictly greater than x. And therefore, y is a limit point of Q. So we have shown that any real number is a limit point of Q, and so the set of limit points for this set is the whole set of real numbers. Now let's look at our next example, the set containing 1, 2, and 3 in the real numbers with the usual metric. This time we're going to employ this theorem from the previous video, that x is a limit point if and only if the distance between x and the set A minus x is equal to 0, a limit point for A. So let's think about this here. Let's let x be any element of the real numbers, and let's think about the distance between the point x and the set 1, 2, 3 minus x. So for example, like if x actually was in the set, like if x was equal to 2, what's the distance between 2 and this set? That would be the set 1 and 3. In this case, that distance would be 1. What if x was just something else? Let's say x was 3.1. Then the distance between 3.1 and this set 1, 2, and 3, we don't need to subtract, well, we can subtract 3.1 from it because it's not in there. The distance there would be 0.1. So basically, this distance is always going to be the minimum between x and whatever elements still remain of this set in the set minus x. And we can see that this is always going to be some positive distance. If x is actually in the set, then the distance is going to be at least 1. If x is not in the set, then it's just the distance between that element and the closest number in the set. And so let's, and just as a reminder, the distance between a point x and a set B is the greatest lower bound of the distances between x and B, such that B is in B. That's the definition of a distance from a point to a set. But if we're talking about a finite number of points, this is just going to be the minimum of such distances. The greatest lower bound is just the minimum because we're talking about a finite number of points. So that tells us that this distance between x and the set 1, 2, 3 minus x is going to be equal to the minimum of these distances between x and let's say A, such that A is in the set 1, 2, 3 minus the point X. And since it's the minimum over all of those points, since all of these points are not equal to the point X, these are all distances greater than 0. So this is going to be strictly larger than 0, the distance between a finite number of things that are not equal to each other. And so by our theorem above, this tells us that any x in the real numbers is not a limit point of this set. So the set of limit points then is the empty set. Now let's look at the set of points 1 over n such that n is in the natural numbers as a subset of R with the usual metric. Again, we're going to use this theorem to think about this. We could also think about it just using the definition of a limit point. So first, let's show that 0 is a limit point of this set. And let's just call this set the set A. So we'll show that 0 is a limit point of A. Now let's think about the distance between the point 0 and the set A minus 0, which is the same as just the set A itself because 0 is not in A. This distance is, as always for a set, the distance between a point and a set, the greatest lower bound of the distance between 0 and A, such that A is in the set A. Again, we could say minus 0 or not, same set. And what is the greatest lower bound of these? The greatest lower bound is going to be 0. To just verify that that's the case, if we let epsilon be greater than 0, then there is some n in the natural numbers such that the distance between 0 and 1 over n is less than epsilon. We know that that is true. So that tells us that this greatest lower bound must be 0. It can't be any value greater than 0. So this cannot be the greatest lower bound. The greatest lower bound is 0. This condition holds, and therefore 0 is a limit point of this set. Now let's show that other values cannot be. So other real numbers cannot be. So maybe an easy case, let's say that x is less than 0. Then the distance between x and this set A, which again will not include x in this case, is going to be greater than or equal to the absolute value of x, right? Because if we're talking about this set, which does not include 0, but includes 1/2 and 1/3 and 1/4 and so on, then if x is less than 0, the distance between this set and the set A, in fact, it's the greatest lower bounds, so it's not even just greater than or equal to 0. The distance between x and A is going to be the absolute value of x, which is greater than 0. So again, employing this condition, that tells us that since the distance between x and the set A, not including x, is greater than 0, and so that tells us that x is not a limit point. Finally, let's assume that x is strictly larger than 0. Let's break this further into two cases. So if x is actually in this set A, then x is equal to 1 over n, some n in the natural numbers. And in this case, then the distance between x and the set A minus the point x would be equal to just 1 over n minus 1 over n plus 1. That's going to be the closest point to x, and that is greater than 0. Since that distance is greater than 0, that means x is not a limit point. So elements of the form 1 over n, elements of this set, are not limit points. And that's kind of interesting property. Now what if, so that's sort of case 1, case 2, when we're assuming that x is greater than 0, if x is not equal to 1 over n for any n in the natural numbers, then it still is the case that there exists some n naught such that x is going to be strictly larger than 1 over n naught. So if x is positive, there's going to be some x, some natural numbers such that x is greater than 1 over that natural number. And what we're going to do is let little m be the minimum of the distances between x and n such that n is less than or equal to n naught. Now let's think about this number line. So 0 is not included in the set A, but we've got 1/2, we've got 1, we've got a third and a fourth, and so on, as being in this set. Let's say that x was 0.27, pretty close to a fourth. Then we could use n naught is 4. That would make the most sense. And we're saying, okay, let's consider the minimum of all these distances of the distance between 0.27 and a fourth, between 0.27 and a third, between 0.27 and a half, and between 0.727 and 1. The minimum of all those distances is going to be the distance between that point and the set, because for everything with n greater than n naught, those are going to be of distance farther away because x is greater than 1 over n naught. What if we'd picked something sort of silly like n equals 100? This statement would still be true, but we'd still have this finite set of, we're looking at all things in this finite set, 1 over 100, 1 over 99, 1 over 98, etc. What's the minimum of the distances between x and those elements? And because we're taking the minimum of a finite set, this minimum is going to exist, and this minimum is going to be greater than 0. So this tells us that the distance, in this case, between x and a minus x is still equal to m, which is greater than 0. And so this tells us that x is not a limit point in this case as well. So this tells us the only limit points of our set A equals 1 over n, such that n is in the natural numbers, is 0. That is our only limit point. Here's our last example. We're looking at the set 0, 1, the open interval from 0 to 1 in the real numbers, now with the discrete metric. So recall the discrete metric is that the distance between x and y is 0 if x and y are equal, and it's 1 if x and y are not equal. Now this set has no limit points. So the set of limit points is the null set. That is our set of limit points. So to justify that, let's let x be an element of the real numbers. Then the distance between the point x and the set A minus x, where A is our set 0, 1. What is the distance? Well, for every element A that is not equal to x, the distance between A and x is 1. So the greatest lower bound of 1, 1, 1, 1, 1, 1, 1, 1 is 1. And since that is greater than 0, that tells us that x is not a limit point of this set. So that's sort of an interesting situation. We saw that in the open interval from 0 to 1 in R with the usual metric, the set of limit points was the closed interval from 0 to 1, whereas here, the set of limit points, if we're talking about the discrete metric, is the empty set. We'll now discuss a theorem that gives the relationship between closed sets and limit points. So here's our theorem. A subset A of a metric space XD is closed if and only if that set A contains all of its limit points. So that's a pretty neat theorem. Let's just remember the definition of limit point on the side. So if XD is a metric space and A is a subset of X, then a point X in X is a limit point of the set A if every open set containing X. So if, when we're talking about our set A, if every open set containing the point X, U open, contains some element A such that A is not equal to X. So that's the definition of limit point. Now let's prove this theorem in the forward direction. So let's suppose that a set A is closed and we want to show that A contains all of its limit points. So we're assuming A is closed. We want to show that A contains all of its limit points. Since A is closed, what's the definition of being closed? That means that its complement is open. That means that A complement is equal to U is an open set. So A complement, we're just calling it U, is equal to an open set. So now instead of this picture over here that we have with a limit point, we have, now we've got still, okay, A is some set that we say is closed. U is equal to X minus A, everything that is in the set X but outside the set A. So all of this is U outside of A. And U is open by definition. A set is closed if its complement is open. All right, so let's now suppose for contradiction that A does not contain all of its limit points. So suppose for contradiction that X is a limit point of A and X is not an element of A. So if X is not an element of A, where does it have to reside? It must reside in A complement. In other words, X must be an element of U. So X is an element of U, which is an open set. And so X is an element of U, U is an open set, and what else do we know about U? U is A complement, and so the intersection of U and A is the empty set, the set of all elements that are both in a set and not in a set and its complement is empty. And so what does that tell us? That tells us that then A is not a limit point, then X is not a limit point of A. How do we know? We know because U is open, contains X, and this criteria does not hold the definition of a limit point. There's this open set U containing X that contains no other elements of A. So there is no element A in the open set U and A minus X. So since there is no such element, that means that X is not a limit point, and because X is not a limit point, this is a contradiction. So where does our contradiction come from? Our contradiction comes from assuming that A is closed and that that X is a limit point that is not in the set. So our contradiction comes from here, and that tells us, therefore, A contains all of its own limit points. Now for the reverse direction, I'm actually going to let that be a homework problem. I promise it is not too hard. It's a little easier than the other direction that we just did. The theorem is stated in the book, and if you want sort of a hint, then the hint refers back to a proof done earlier for just the real numbers. So, hint in the book, if you take a look at the statement of this theorem in 3.2, it's also similar to a proof from chapter 2. So you might not need this hint at all, but if you want, you can definitely take a look. All right, so we know that a set is closed if and only if it contains all of its limit points. So, previously we just had a definition, a set A closed, if and only if. Any definition is if and only if a complement is open. So that was our previous definition. And now we also have a new thing that is true about a set A. A set A is closed if and only if it contains all limit points. So, let's think about, for example, some of the examples we looked at earlier. So let's say the set 1 over n, such that n is in the natural numbers. Let's think about the set 1, 2, and 3. Let's maybe leave it at those two sets. So are these sets closed? So think for a second about whether or not those sets are closed. And pause. Okay, so the set 1 over n, such that n is in the natural numbers, the only limit point was 0. So the only limit point of this in the real numbers with the usual metric is 0. And 0 is not an element of the set, not an element of the set 1 over n. And so this tells us that this is not a closed set. So it's not a closed set. That doesn't necessarily tell us that it's an open set either, right? A set is closed if its complement is open, but a set can be either both open and closed, or neither open nor closed, or one and not the other. So this set is not closed because it does not contain all of its limit points. This doesn't immediately tell us anything about whether or not the set is open. Now, what about the set 1, 2, and 3? What were the limit points? We saw that the limit points of this set were just the empty set. There are no limit points for this set. And because it has no limit points, does this set contain all of its limit points? Yes, it is vacuously true that this set contains all of its limit points, that the empty set is a subset of the set containing 1, 2, and 3. And because of that, that means that the set 1, 2, 3 is closed.